Hello everyone, today we're going to look at Lesson 30, Simplifying Radicals. We'll start off with some basics. We have the square root of 25. Most of us already know that that's 5, but let's see why it's 5. So I'm going to rewrite 25 as 5 squared. So I have the square root of 5 squared. The square root is what we call the function that undoes the square. So if I'm undoing the square, what I'm left with is 5. So as another example, the square root of 16. I can rewrite 16 as 4 squared. So I have the square root of 4 squared. Again, they cancel, and I'm left with 4. Now let's look at it in more general terms. The square root of x squared is x, assuming x is positive or 0, which we will assume from now until pretty much the end of the quarter. So anytime we have the square root of a variable, we're going to assume that variable is in fact positive. So let's look at the more general case, the square root of x to the 2n. So the square root of x to an even power. Right? Any even number I can rewrite as 2 times the number. So when I see 2n, I'm thinking of an even number. Using the rules of exponents, I can rewrite x to the 2n as x to the n squared. So remember, rules of exponents will tell me that in order to do x to the n squared, I'm going to multiply my exponents, and I'm going to get back what I started with, x to the 2n. So these two things are equal. And then again, the square root and the square cancel each other out, so I'm left with x to the n. So if I'm square rooting something to an even power, I keep the same base. Right, x is still x, that hasn't changed. The only thing that's changed is I've gotten rid of the square root and I've cut my exponent in half. So let's see an example with some actual numbers. Okay, so example, the square root of 16 to the 6. I get rid of the square root, I keep the base, and the exponent gets divided by 2. So the square root of 16 to the 6th equals 16 cubed. So again, the base is the base, it doesn't change, it's still 16. As another example, the square root of 4 to the 20th. So again, I'm going to get rid of the square root symbol, and I'm going to take my exponent and divide it in 2, and I'm going to get 4 to the 10th. So let's do a couple more. Simplify the following. A, the square root of z to the 30th. So again, 30 is even, so I can just divide it by 2 and get z to the 15th. Sometimes we'll have more than one factor inside the square root. So for B, we're going to look at the square root of x to the 4th, y to the 8th, z to the 12th. So again, each of these exponents are even, so I can just divide them by 2. So I no longer have the square root. I've got x squared, y to the 4th, z to the 6th. For example C, I have the square root of 7 to the 16th. So again, 7 is just my base, that doesn't change. All I'm going to do is divide the 16 by 2 and get rid of the square root. So I'm left with 7 to the 8th. Let's do a couple more. D, the square root of 10 to the 20th. I'm left with 10 to the 10th. So again, take the 20, divide by 2, get rid of the square root. I can have a mixture of numbers and variables. So the square root of 25 to the 4th, x squared. Divide each of my exponents by 2, get rid of the square root. I'm left with 25 squared x, which I can further simplify to 625x, because 25 squared is 625. And my last example, the square root of 68 to the 24th, a to the 30th. Again, each of those exponents are even, so I divide by 2. 68 to the 12th times a to the 15th. I'm not going to find out what 68 to the 12th is, that's way too big, so I'm going to leave it in exponential form. Now we're going to look at what happens if the exponent is odd. Any odd number I can rewrite as 2n plus 1. So I'm thinking of an odd number, I think of 2n plus 1. And what I'm going to do is I'm going to again use the rules of exponents and rewrite x to the 2n plus 1 as x to the 2n times x. So I'm going to pull out the x, so one of the x's. So if I look at it all together, I have the square root of x to the 2n plus 1, which equals the square root of x to the 2n times x, which I can then separate using, again, rules of exponents to the square root of x to the 2n times the square root of x. Square root of x to the 2n is x to the n, so I'm left with x to the n times the square root of x. So again, this is going to be the idea. We're going to pull out one of our factors. What we're left with is an even power. I can use the rules from a couple minutes ago to simplify that part. And I'm always going to be left with the square root of one of whatever my base is. So as an example, the square root of x to the 7th. I can rewrite that as the square root of x to the 6th times x, separate it across the square root symbol, and then simplify. So the square root of x to the 6th becomes x cubed, and I still have the square root of x. My next example, the square root of 3 to the 5th. So again, I'm going to break it down into the square root of 3 to the 4th times the square root of 3. So I've combined these two steps into one. And then I simplify the square root of 3 to the 4th as 3 squared times root 3. And then we know that 3 squared is 9. So the square root of 3 to the 5th is 9 root 3. So let's do some more practice with this when our exponents are odd. So question A, the square root of z to the 9th. We know that 9 is 8 plus 1. So we're going to look at z to the 8th times z, and I can square root z to the 8th and get z to the 4th times z. The next one is we have the square root of x to the 4th, y cubed, z to the 11th. X to the 4th, that's all writing even exponent, so I can just pull it out and divide it by 2. Y cubed, I can think of as y squared times y. And z to the 11th, I can think of as z to the 10th times z. And all those even ones, again, I can pull out when I divide it by 2. And I'm left with x squared, y to the 1, z to the 5th, and I still have the square root of my y and z, because those are my variables with the odd exponents. Part C is the square root of 7 to the 15th. Again, 15 is 14 plus 1. I take the 14, divide that by 2, and I've got 7 to the 7th times the square root of 7. So my next one, I have the square root of 16x to the 31. Root 16, I can simplify because that's 4. And then x to the 31. 31 is 30 plus 1. Take my 30 out by dividing by 2. And I'm left with 4x to the 15th square root of x. My next one is the square root of 4y to the 101. So again, root 4, I know what that is, that's 2. And then 101 is 100 plus 1. Take out the y to the 100 out of the square root as a y to the 50th. So I've got 2y to the 50th square root of y. And as the last example for the odds, I've got the square root of 68 to the 29th, a to the 23rd. So again, the 29 is 28 plus 1. 23 is 22 plus 1. Divide those even ones by 2. And I'm left with 68 to the 14th, a to the 11th, square root of 68 times a. The last thing we're going to talk about is what if the integrand isn't in exponent form? So I've got something like square root of 20, square root of 50, square root of 48. The question is, can we still simplify, not round, not plug into the calculator and come up with some crazy decimal, but just simplify them? And the answer is typically yes. So what we're going to do is we're going to take our square root of 20 and we're going to ask ourselves, what is a factor of 20 that's a perfect square? So it has to be a factor, so something times something equals 20, and at least one of those has to be a perfect square. Our goal is to look for the largest one. So hopefully we recognize that 20 is 4 times 5. So I'm going to rewrite 20 as 4 times 5, and then use rules of exponents. I'm going to separate my radical into root 4 times root 5. Root 4 we can simplify, and we get 2 root 5. So then we'll do the next one, root 50. Is there a factor of 50 that's a perfect square? Yes. 50 is 25 times 2. So then we're going to split it up across the square root symbol and simplify because we know what the square root of 25 is. We're left with 5 root 2. So you have to be really careful and remember which factor is actually in the square root, because these two look very similar, but they are in fact very different, right? 2 root 5 is the square root of 20, 5 root 2 is the square root of 50. So make sure that you're putting the correct number outside the square root and the correct number inside the square root. Square root of 48. So again, is there a factor of 48 that's a perfect square? The answer is yes. 48 is 16 times 3. Now you might not notice 16 right away. You might have just said to yourself 4. 4 is a factor of 48 and it's a square, but it's not the biggest. And in fact, 16 is. So again, 48 is 16 times 3. So I separate it across the square root. And again, I know what the square root of 16 is. It's 4. What about the square root of 450? So this is a fairly high number. So again, you might not find the largest square root first. So let's say we do notice that 9 goes into it. Right? I know that 9 goes into 45, so I know it's got to go into 450. So I rewrite it as 9 times 50. And I separate it and say, okay, I know what root 9 is. I know that's 3. But then I see what I have left, square root of 50. Can I simplify the square root of 50? Yes. We already did it. So I'm going to break down 450 as 9 times 25 times 2. Square root what I know that I can square root. So 3 times 5 times root 2. And then multiply and get 15 root 2. So you don't have to find the largest square root first. You just have to find a square root and then look at what you have left over and start again from there. So the next couple examples, once I show you the example A, root 80, pause it and see if you can simplify it on your own first, and then we'll check back when hitting play. So can you think of a perfect square that's a factor of 80? Hopefully yes. So again, pause it if you haven't yet, try it on your own, and then when you found it, unpause it. So 80 is 16 times 5. Square root of 16 is 4, square root of 5 is square root of 5, so we get square root of 80 is 4 square roots of 5. Square root of 128. So again, hopefully you're finding this on your own first. And again, if you don't find the largest right away, it's okay. Just keep going until you're sure that whatever is left over doesn't have a factor that's a perfect square. So 128 is 64 times 2, and the square root of 64 is 8. So we get 8 root 2. C is the square root of 75. A perfect square of 75. A perfect square that is a factor of 75. So is there a factor of 75 that's a perfect square? Yes, 25. So 75 is 25 times 3, And again, we know what the square root of 25 is. So we get 5 root 3. D, the square root of 8. This is the one that people tend to forget about, and they'll say that it's fully simplified and be done with it. But there is a factor of 8 that's a perfect square, and that's 4. So again, we square root 4 and we get 2, and we're left with 2 root 2. So just because 8 is a one-digit number doesn't mean that it's fully simplified. So root 8 is 2 root 2. And then the last one, the square root of 54. That is the square root of 9 times 6, and that equals 3 root 6. So let me know if you have any questions on it. Otherwise, try the homework and let's see how you do.